The talk will be given by Professor Bogdan Rosa, who was invited to talk about computational modeling of the cloud microphysical processes. And Professor Rosa, he works in the Institute of Meteorology and Water Management, and this is institution which is responsible for providing official forecasts for Poland. Bogdan, can you start?
Yes, thank you, Chair, for your nice introduction. It's a great pleasure to present my research to such a competent and experienced audience. Yes, as Karolina said, I work for Polish Weather Service, and our main activity is the development of reliable weather forecasts. The forecasts are simulated using advanced NWP systems. Currently, we use operationally two models that are Cosmo and Aladeum. So for reliable weather or climate prediction, we need to provide to such models accurate description of cloud microphysical processes and also large-scale cloud dynamics. And the microphysical processes, unfortunately, cannot be fully resolved in NWP systems. That's because their characteristic length scales are much smaller than the grid spacing of those models. So the common strategy, common approach is to represent only some statistical features of the droplet dynamics, and we call it as parameterizations. But to develop such parameterization, realistic parameterization, we first to have quantify those processes, and we may get this knowledge from numerical simulations. My research I was carrying on are focused on evaluation of different effects on the collision statistics. By collision statistics, I understand, for example, radial distribution function, which is the measure of droplet clustering, and radial relative velocity between the droplets. Another important quantity is the settling velocity. So those parameters may depend on different factors. For example, range of the turbulent scales, which can be defined by a single parameter like Reynolds number, or in other words, size of the computational domain. We know that the distribution of the droplets inside the cloud is not uniform. That's because of centrifugal force push the droplets outside of the eddies. So in some places, some regions, there are clusters. And the clusters may affect turbulent flow. So the question is whether we should use one-way momentum coupling in such simulation, or two-way momentum coupling is more precise. If we want to consider aerodynamic interaction, of course, this is another important element. For very short separation droplets, between droplets for approaching or receding, there is another important factor, which is lubrication forces, and gravity, and then some also other components. So the goal is to compute collision rate, because this is the parameter which defines the rate of the rain droplets formation. And in kinematic formulation, this collision kernel, which is proportional to the collision rate, is basically product of the relative velocity between the droplets and radial distribution function. Addressing to each of those problems is a serious scientific challenge, and for modeling, we should use thinking out of the box and advanced computational methods along with the high-performance computers. Cloud physics is a multi-scale problem, so there is no single tool that can be used for modeling different effects across such wide range of scales. You see that the length of scale changing 13 or even more orders of the magnitude. But even for modeling microphysical processes, that is hard to find one generic tool. That's because we should represent both short-range aerodynamic interaction as well interaction of the droplets with the eddies that belong to the dissipation range of energy spectra, and even some portion of the inertial range of the energy spectrum. For modeling dynamics of that single cloud, more appropriate are LES method. Then we have the range characteristic for NWP, where the grid spacing is of order of 1 kilometer. So modeling cloud microphysical process is challenging task because the processes are represented by different by wide range of length scales. Here we see a brief overview of different computational approaches. Each of them has some advantages and disadvantages. The very basic are large eddy simulation, which are appropriate for modeling dynamics of large inertia droplets. That's because large droplets interact with larger eddies, and they are explicitly represented in such a simulation. For modeling dynamics of lower inertia droplets, we should use DNS under one-way coupling, or if there is significant mass loading, we should use DNS under two-way momentum coupling. If there is a large volume fraction of the droplet, then we should use also some parameterization of collision elastic or inelastic. So then the more appropriate is DNS under four-way coupling. For representing aerodynamic interaction and the turbulent flow, the recommended are hybrid direct numerical simulation. Currently, we work on HDNS along with the lubrication effects. And the most precise and more realistic are simulation fully resolved or LBM methods, lattice Boltzmann method, but they are computationally expensive and are limited to very small number of droplets. And there is a short literature review concerning modeling of cloud microphysical processes. So first, rigorous simulation under two-way momentum coupling were done by Squires and Eaton 30 years ago. Then when the computational power increases and we have access to more powerful machines, the resolution increases up to 2000, and the very recent were done at even 8000 cube grid points. So they became more and more advanced and more realistic. But performing simulation at high resolution meshes with under two-way momentum coupling is problematic because we have to keep we have to track large number of droplets. So in very recent study in 2017, Mochon and Dejuan performed the simulation under two-way momentum coupling at relatively coarse resolution. So today I will address 4 specific questions that are related to the modeling cloud microphysical processes. So the first question is why we need high resolution direct numerical simulation, and can large eddy simulation, which are much cheaper, be as accurate as DNS? Is the effect of two-way coupling really important? How the droplets affect the turbulent flow, and what's the impact on the collision statistic? And the last question is what's the effect of aerodynamic interaction? For more complete information, I refer you to my publications. So our research tool are numerical simulation. We use standard Eulerian Lagrangian approach. For modeling turbulent flow, we use Eulerian approach. So we solve this Navier-Stokes equation on regular mesh. That's the equation 1 is and 2, that's the standard Navier-Stokes equation in compressible form. It has two additional factors. One is the forcing term, which enforce and maintain turbulent flow, and the last forcing, Fp, is the forcing coming from the droplets if we consider two-way momentum coupling. So if we have two-way momentum coupling, there is a problem because the flow is not divergent free. But this effect can be safely neglected if the volume fraction is smaller than 10 to minus 3, or that's the case in all our simulation. Another problem is the mean flow, because the settling droplets may enforce the turbulence, may enforce the flow along the gravity direction. So this problem is artificially solved by putting 0 to the zero wave number in the Fourier space. And we solved this Navier-Stokes equation using pseudo-spectral method. For LES, we use basically the same code. So equation 1 transferred to the Fourier space is given by equation 6, which has one extra term. It's mu E, which is effective viscosity. If we want to solve this Navier-Stokes equation on coarse mesh, there is a problem because the code may diverge, solution may explode. So we need to add this extra viscosity, which depends on the energy at given critical wave number and this analytical expression given by equation 8. So on the figure, on the bottom figure, you see how the vorticity flow field looks like from our simulation. And on the right-hand side, you may see comparison of energy spectra from DNS. This is black line, and LES, which is plotted using this red line. So in DNS, we are able to cover wider range of energy spectrum. For modeling droplet dynamic, we use a standard Lagrangian approach. Motion of droplets is governed by Stokes drag, gravity, inertia, and in some cases, aerodynamic interaction. We have again periodic boundary condition, and we use this physical quantities for physical values for density and gravity. So what's the range of applicability of the pseudospectral method for modeling turbulent flow? We know that in cloud, the Reynolds number is in the range between 1,000 up to 10,000. But in DNS, this Reynolds number depends on the mesh resolution. And maximally, we may reach about 500. So it's smaller. But the good news is that the droplets interact mainly with smaller eddies. That's this range should be sufficient, at least for smaller inertia droplets. So for modeling turbulent flow at coarse resolution, we may use a very simple code parallelizing OpenMP. And then at some point, I developed the code which based on the 1D domain decomposition and MPI library, and currently we use massively parallel code, which is based on 2D domain decomposition. For such complex simulation, we need a large computational resources. So 10 years ago, I used the state-of-the-art machine provided by National Center for Atmospheric Research, and then we switched to the computers at Interdisciplinary Center for Mathematical and Computational Modeling. So you see the comparison of those machines in last 10 years. The computational power increases 20 times. And what is interesting that the power consumption is on the same level or even smaller. So now I want to tell something about result. On the left side, you see the two figures. Those represent average settling velocity in the domain, the computational domain, divided by the terminal velocity. Terminal velocity is the settling velocity of the droplets in the stagnant air. So for low inertial droplets, it's one. That's because small droplets, they behave like fluid elements, and the average velocity in the domain is 0. So there is no increase. For large droplets, the turbulence does not play the role. Yes, like for example, cannonball. The interesting region is between 10 and 60 microns, and we observe some increase in the settling velocity. If we plot the same data as the function of Reynolds number or grid resolution, we see that this for some droplets we observe already saturation, and for heavier droplets we see only little enhancement. So for low inertia droplet, there is no need to run the code at larger meshes, but for heavy droplets, we need to perform the simulation at even larger domains. And the same situation is with the collision kernel. The plot on the right shows the collision kernel as a function of Reynolds number or mesh resolution. So you see that once the mesh resolution increases, this parameter increases. That's because we are able to simulate larger eddies. The smaller eddies are limited by the grid spacing, but the larger eddies are limited by the domain size. So for 45 for the droplets, 45 micrometer in radius, there is no need to perform simulation at larger meshes, but it's needed for heavier droplets. So can LES replace DNS, can be as accurate as DNS? The answer is on this slide. So let's be focused only on the solid lines and left panel. So two solid lines, black and blue, shows the results from DNS performed at different Reynolds numbers. So we observe only differences for the larger droplets. That's because the larger droplets interact with a broader range of energy spectrum. That's expected, but for smaller droplets, we observe significant difference between the red lines, which represent results from large eddy simulation, and the black lines. However, the simulation were performed for the same Reynolds number. So this difference is due to the some shortcomings in the subgrid scale model. A similar situation we have with the radial distribution function. For larger droplets, for heavy droplets, the DNS results converge to the LES results, but for smaller droplets, we need more realistic subgrid scale model. Okay, so those results shows simulation with two-way momentum coupling. On the top row, we have simulation without gravity. On the bottom row, we have results from simulation with gravity. So first panel shows the radial distribution function, which is the measure of clustering. Then we have relative velocity and the snapshot from the velocity flow field along with the distribution of the droplets. So if the gravity is neglected, we observe that the radial distribution function or clustering decreases with mass loading. That's because the such system behave like system with larger effective viscosity. So the droplets suppress the eddies, which are main mechanism for the droplet clustering. Does not significantly affect the relative velocity. But if we have gravity, the settling droplets may enhance the turbulent flow. So they may generate new vertical structure, which for some droplets or low inertial droplets, like for example 20 microns, we observe some enhancement in the radial distribution function. And once the mass loading increases, we have more and more energetic eddies, and it results in the correlation in the droplets motion, so the relative velocity between droplets significantly increases. So those simulations were done under one-way momentum coupling. How to include the effect of two-way momentum coupling? So we know the solution for the Stokes flow. It means the flow around a single droplet. So we may we can make a superposition of the two solutions with small u1 is the velocity acting on the droplet 1, resulting from the motion of droplet 2, and US is the Stokes solution for flow around a single droplet. So because this Stokes solution is linear in the velocity, we have basically system of two equations with two unknowns, which can be easily solved. But if we have more droplets, then we have sum up the contribution from each of the droplets acting on the droplet of interest. So the system increases, and the number of equations is equal to the number of droplets we consider. If we have additional turbulent flow, we should also include this effect of the turbulence. So finally it comes down to the improved superposition method, which if we make some manipulation with the equation number 4, we move the unknowns to the left-hand side. It's basically a linear system of equation which we may solve using, for example, generalized minimal residual method. But this superposition method does not allow us to represent lubrication effects. That's because they are superposition of flows for a single droplets, around single droplets. So if we want to represent lubrication effect, we have to use the full solution for two droplets. And this is much more complex problem which also includes the effect of rotation. But even if we neglect effect of rotation, the system became smaller. But the analytical solution is given in terms of infinite series, and the series are terms of the series are a solution of non-trivial recurrence relations. And if we consider particle aerodynamic interaction, there is another problem, because the droplets may be located in different subdomains and they interact with each other. So there is advanced exchanging data between different blocks of memory. It has to be intelligently arranged. So that's the results from the simulation with the aerodynamic interaction and with lubrication forces. Again, we consider relative velocity, radial distribution function, and collision kernel. We see that this lubrication affects significantly the relative velocity, but only low Stokes number. But this does not have meaning on the gamma, because the events are very rare. That is hard to find the two droplets close to each other. So what represents the G function. But yes, this lubrication force and aerodynamic interaction is mainly can be seen for the clustering of droplets, and it's reduced the collision kernel and collision rate about 20%, droplets with the Stokes number about 1. So that's my last slide. There are some conclusions from my talk. I just want to mention about other problems that should be addressed in the future. It's molecular effect and continuum lubrication forces, impact of water circulation inside the droplets on their collision statistics or collision efficiency, and effect of viscosity ratio on the droplets aerodynamic interaction. Thank you very much for your attention.
Thank you very much, Bogdan. Are there any questions? I'm really hoping to strengthen our cooperation between ICM and Institution of Meteorological and Meteorology and Water Management. Okay, I cannot see any questions, but if there are any, please write them on the chat, and I'm pretty sure Bogdan will reply.
This cooperation already exists, because we use supercomputers.
I know. Yes, and we also we also deliver our forecasts to your institution in operational mode. So I hope that they are helpful. Okay, thank you very much.